When learning metabolism, it can be really hard to keep things straight, especially because, well, metabolism isn't straight pathways. Instead, it's more of an interconnected web. When you're learning, however, it's important to kind of keep track of everything that's going on and some of the key information about it. Things like where reactions are happening, where we see them, what different pathways are they involved in, how are they regulated, and other key information. I think that keeping a table like this helps you keep track of all the information about specific reactions, as well as keeping in mind how those reactions can be used in multiple pathways, and how the same intermediates can be used in multiple pathways if you take them different directions. So I made this spreadsheet that I'll share that hopefully will help you keep track of these processes as you're learning them. I have a couple of example rows filled out, but then as you learn, you can keep adding and adding to the table. And as you find different instances of an intermediate pop up, say, well, then you can add a row in your common intermediates table. We're saying, oh yeah, we can also do this with that. And then keeping the whole big picture overview, when do we want to do various processes? And like, why might we want to go one direction versus another? As to how you actually go one direction versus another, well, then we have to get down into the nitty gritty, things like our allosteric regulators and hormonal control of these individual steps. So what I recommend is keeping a chart like this, where in this case, I have this glucose metabolism. So I have a page where I have all the different reactions that I know about, that I've learned about with glycolysis, gluconeogenesis, pentose phosphate pathway, glycogenesis, all those different things, and how they interrelate with one another comes into play both in this spreadsheet as well as in like common intermediates, because we can take things in different directions. Here's just one example row, but then I encourage you to fill in the rest yourselves. I found that making it was really, really helpful to me learning, and also to just like keep track of things along the way. And a great review if you're trying to study for finals or something like this. And another great thing about this is that once you have it all written down, well, now you have a great resource you can keep referring to in the future. Here's one example of how I would format something. This example is looking at the hexokinase or glucokinase step in glycolysis or glycogenesis. Basically, you're trapping, and also the pentose phosphate pathway. So it's important to keep in mind like all the different places that you might want to do this. So keep in mind the pathway of the processes, and then the enzyme name. It's important to kind of know the enzyme name because that's often how we're going to be regulating things, especially when we have one of these steps that is quote unquote irreversible. That is, it has such a large negative delta G that it's really, really hard to go back from. And so instead of trying to go back, you control going in that direction, and then you use a different enzyme to go the other direction. If you have a reaction that's running more close to equilibrium, one of those easily reversible reactions, well, then you can control things based on concentrations more easily. Whereas in the case of these key steps with these big energy differences, these are going to drive the pathway forward in one direction, and they're also going to be basically you can't control the concentrations in order and have a big enough effect to change the direction. So instead, we can regulate them allosterically, so we can write down the allosteric regulators, both positive and negative, as well as hormonally. So if we say have insulin increase the localization of glucose importers to the plasma membrane, or we have a hormone that phosphorylates one of the enzymes involved, or that leads to a signaling cascade that phosphorylates one of the enzymes involved. We also want to keep track of like how much are we using energy? Are we getting energy? I mean, in terms of like, are we producing ATP or using ATP? It's helpful to think in terms of ATP equivalents. So say if you go from ATP to AMP, that would be 2 ATP equivalents, versus going from ATP to ADP, that would just be 1 ATP equivalent. Because, well, if you go to AMP, well, now you have to spend an ATP to make an ADP. And so then you have to spend an ATP to make an ATP. So you have to use 2 ATPs to regenerate it. Okay, so those are some of the key things. As well as, do you want to know, like, where is it happening, both inside of cells? So is it happening in the cytoplasm? Is it happening in the matrix? This is going to be really important because, well, some processes need to go between the matrix and the cytosol, but the intermediates can't get out. So it's also important to have in your chart, keep track of things like various reactions that we do to shuttle things through membranes. Okay, is this specific to various tissues? And are there other notes? Or are there things like cofactors that are required? Are there just other cool things that you learned about? Any other kind of things that don't fit directly into one of these other columns? Now what you could do is you could add on further steps. So you could say have one that is for the glycogenolysis, or for in your liver, or for the gluconeogenesis in your liver, where basically you need to let the glucose out after you phosphorylate it. Okay, common intermediates. I think this is one of the most important sheets. Here you can basically take one intermediate. So when we talk about these metabolic intermediates, it's just like one of these molecules that's in a pathway. You can do things to it. You can make it different ways, all these various things. So we call it an intermediate. And it's often an intermediate in multiple pathways. Either pathways that use the same enzyme or pathways that actually take that intermediate and do something completely different with it. A good example of this is dihydroxyacetone phosphate, or DHAP. We're typically more used to seeing it as just like, oh, that's that part in glycolysis that we want to get rid of, that we channel things using triose phosphate isomerase to turn it into G3P, glyceraldehyde 3-phosphate, that then continues on into glycolysis. And that allows us to basically use that payback phase of glycolysis to do the same thing 2 times versus having to handle 2 different 3-carbon units. But one of the other functions of this is that it provides a way for glycerol from lipids to enter glycolysis for further breakdown. Because when you have glycerol, well, it can convert to dihydroxyacetone phosphate, and using the glycerol 3-phosphate dehydrogenase. And then this is going to, once we have the dihydroxyacetone phosphate, we can convert it into our G3P, which can continue on into glycolysis. Doing that glycerol 3-phosphate to our dihydroxyacetone phosphate, well, that's also a way that we see that we can get reducing equivalents from the cytoplasm to Q. Because we're generating NADH in glycolysis in the cytoplasm, but we can't get it into the matrix directly. And so the glycerol 3-phosphate shuttle is one of the ways that we can sneak those electrons in. We also can talk about, like, okay, well, how do we generate dihydroxyacetone phosphate? One of the other ways we can generate it is by splitting a 6-carbon F16BP into 2 3-carbon parts. And then if we want to join 3-carbon parts together, well, now we can do that. We can take a dihydroxyacetone phosphate, join it up with the G3P, and voila. Well, now we've got our F16BP. We can continue on to in our gluconeogenesis and things. So this is an example of kind of how you can make a common intermediates pathway and then just add another row whenever you learn about a new thing you can do to that. Or you can add a new roller function to the same reaction when you learn, oh yeah, we also see that here. And then finally, just kind of like an overview of, although yes, they're not really pathways, they're kind of more interconnected webs. When would we want to go in which direction? Under what physiological conditions? What are kind of key regulatory points? Where is this happening? When is this happening? All that good stuff. So yes, metabolism can seem really, really complicated, but hopefully by focusing on kind of some of the key things and keeping track of, trying to keep track of it all, it can be a really helpful way to help you see how things are interconnected and how you can go all these various directions. But things typically, once you kind of get the logic down, they make sense.